Good afternoon, everybody. Welcome to another session of EI Live for K-12 students and educators, brought to you by the Earth Institute at Columbia University. My name is Cassie, and I'm the director for the Office of Education and Outreach. And one of the biggest parts of my job is to bring our scientific research to different audiences, including students and teachers. So for those of you who aren't familiar with the Earth Institute, our core mission is to foster a greater understanding of the science behind sustainability and the climate crisis and what we as global citizens can do. There are a lot of different experts that make up the Earth Institute, including business and policy experts, earth scientists, economists, and specialists in public health and law. The Institute is made up of 24 research centers and several hundred people who collaborate across many different disciplines and schools within Columbia University. What we're hoping to do with these sessions is to introduce you to the interdisciplinary work that we do through our experts. So we'll have sessions until the end of June for K-12 students and educators, and we'll also have some additional sessions this summer that we'll be sharing information about very soon. So today we're going to hear from Laurel Zyma and Margie Turin, who both work for Lamont-Doherty Earth Observatory, which is one of the units, the largest unit of the Earth Institute. So Laurel is an educational program assistant, and Margie is the director of educational field programs. Today they're going to help us explore sea level rise through the Polar Explorer app in order to help us understand the drivers and impacts of sea level changes, both locally and globally. So for those of you who are using Zoom webinar for the first time, we're going to be using the Q&A box, not the chat box. And the Q&A box is going to be where our presenters are going to ask you some questions while they're presenting, and you can use that box to answer those questions. And that's also where you can type in questions that you have. And you can do that as soon as the presentation starts. You don't have to wait till the end. We're going to be monitoring that Q&A box throughout, so we don't leave any questions left unanswered. So type in your question at any given point for our presenters. Once the session is done, what we'll do is share a link with everyone who is registered for the event so that you can access the recording later on when it's posted to YouTube. So email me directly at the email that you received this Zoom webinar link for if you have any technical difficulties, or if you don't want to use the Q&A box or you're having issues, you can just send me an email with a question and I'd be happy to help facilitate. So without further ado, here is Laurel and Margie. All right.
Great, thank you. I'm Margie Turin, and Director of Educational Field Programs, and I wanted to introduce you to an app that we developed as part of a climate project that we're doing. It's called Polar Explorer Sea Level. But before I do that, I want to tell you that we do a lot of work about climate and work a lot in the polar regions. And that is a really fun and exciting part of my job. And I wanted to give Laurel a chance to introduce herself.
Hi, everyone. My name is Laurel Zyma. I work as the educational program assistant. So I work very closely with Margie and Cassie at Lamont-Doherty Earth Observatory. We have the pleasure of working with the Polar Geophysics group at Lamont. And so we're helping to take their research and their area of study and make it accessible to students, teachers, and the public. So you'll be learning a lot today about sea level rise.
Okay, well, we're going to start right in with a question for everybody. So I'm going to ask you if you do you live in a coastal shoreline county? So by a coastal shoreline county, I'm asking if you live on the coastline of an ocean, an estuary, or a Great Lake. And I want you to answer yes or no. So Cassie, I'm having a little bit of a challenge in terms of seeing the responses to the question. If I'm
Oh yeah.
be able to.
Yep. I'm still there. So they're still coming in. So
Okay.
I'm giving that a second here. Okay. So it looks like about most of our participants, so 65% of our participants are saying no, and 35% of the participants are saying yes to the question.
So 35% of our participants say that their county is on a coastal shoreline, which means that their county is on the ocean, an estuary, or Great Lake. Okay, this is terrific. This is exactly what we wanted to know. And what I was interested in doing is situating you in terms of how the United States population is situated. So this is a bit of data that we'll walk through very quickly. So 10% of the United States coastal counties are actually on a coastal shoreline. So 10%. So that means 90% of the US is not on a coastal edge. But 39% of our population actually lives in that 10%. So very disproportionate. If you expanded that to coastal watersheds, so areas that actually drain into an ocean, an estuary, or Great Lake, you get 20% of our land area, but you get 52% of our population, so over half of our population. So basically, our coastlines are a magnet. People love to be there. Our group is a little non-representative, perhaps, well, actually very close, because we asked for coastal counties, so 39%, it's about right, right? And down at the bottom, I want to point out this really cool infographic. So basically, this box represents a square mile, and each one of these peoples represents 10 individuals. So in 1 square mile in our coastal counties, 446 people reside versus 319 in this coastal watershed areas. And then you get to 105 if you get to more inland areas. So we're very much disproportionately represented on our coastlines, which is an important thing to think about as we go forward with this time together. This is pointing, by the way, this data is from the 2010 census, which is our most recent census. We're in the middle of a census right now, and the expectation is that with this new census data, this will only get worse. So we'll have about 8% more people on those coastal areas. And this data that I just popped up on the right shows you that in just 40 years, so from 1970 to 2010, those numbers increased dramatically. So again, I think the takeaway here is that we want to remember that our coastal areas are magnets. Okay, so how would you define sea level? And do we think sea level is the same everywhere? I just want you to think about that for a minute. And then we'll just pop right into answering it. No, it is not the same everywhere. There are 2 main differences or designations of sea level. We have what's called absolute sea level, and we have relative sea level. So absolute sea level is looking at things that are more global in how they affect sea level. So we're looking at the larger ocean and any dynamic that actually affects that. So a good example of a dynamic that would affect absolute sea level would be a melting of ice sheets. That goes into the larger ocean area and would affect everywhere. Granted, it doesn't affect everywhere exactly the same, but everybody's affected by that process. Whereas relative sea level is looking at a very local relationship with the ocean. So it's where the ocean actually connects with the land in a very specific place. And there are a lot of things that can affect that. Everything from the land subsidence or settling down around the coastal region, to different circulation patterns in the ocean, to the response of the land to having lost ice in the past. Any number of changes can affect a specific area. And so when you're looking at sea level, it's important to pay attention to whether people are talking about absolute or relative. And we'll have graphs that have both of those things in them today, so just something to pay attention to as we move forward. And again, just to pop this up, so absolute is global with uniform impacts, and relative is local with specific impacts. Okay, so why are we focusing on sea level? This is a wonderful image that was snapped by by NASA from space. And you can see by looking at this that the oceans and water just dominate our Earth system. In fact, water covers, in some shape or form, covers 75% of our Earth's globe. So 3/4 of it, if you want to think about it that way, it's a lot of our Earth's surface that's covered in this way. The ocean itself covers about 71% of the Earth's surface. So just breaking down how this water is separated, 96.5% of the water that's on Earth is in oceans. Only 1.7%, so less than 2%, is in lakes, rivers, streams, and tied up in the soil as groundwater, etc. I think a lot of people are surprised to think that only 1.7% is tied up in ice, and that's all the permanent ice that we're thinking about on Earth. So our ice sheets, our glaciers, our permanent snow. But that 1.7%, I want you to pay attention to, because it can have a big impact, and Laura will talk about that a little bit later. And then the last part of this cycle or system that we have, the hydrosphere, which is what we refer to as our Earth's water, is in water vapor. And that's really a very small amount. So it's 1/1000%, so very, very small percent. So most of it is actually in our oceans. It's also interesting to think that a hydrosphere is in balance. And there's been the same total amount of water on the Earth for millions of years. So I always like to think about the fact that this Tyrannosaurus rex could have been drinking the same water that I'm drinking out of my water glass right now. Kind of an interesting way to think about it. So that water is persistent, it's been here, but it's not always in the same form. So sometimes it might be in ice, sometimes it might be in the ocean, sometimes it might be in groundwater, but that water is the same as it's always been. So this is a graph that I want you to look at, think about, and perhaps think about what do you think the driver for this change in sea level was. So let's talk through and look at this graph first of all. So this is a generalized curve of sea level rise over the last 21,000 years. So if you look at the x-axis and follow along, we're following 0 is all the way on the right, and we're going back in time as we move to the left. You'll see the word relative sea level here on the y-axis. So we just talked about relative, which meant local. So where in the world are we when we're looking at this graph? This is a graph of the eastern United States. So this is a local to our area. So Columbia is in New York. So I picked this graph because this is talking about our specific area. And you'll look, this is in meters of sea level change. So you look and see that it was 120 meters lower than present if we went back 25,000 years ago. So considerably different. What do we think happened? What do you think were the drivers that caused this to change? Well, if we think about it, there was an ice age, and that ice age got to its maximum extent around 22,000 years ago, and then it started to change. And as it changed and started to melt, we saw that ice transition into our oceans. And so as it moved into the oceans, you'll see that steadily through time, the oceans started to rise. This is a process that has occurred many times in our past. So it's just that moving of water from a frozen state into a liquid state. And this movement occurred fairly steadily until about 6,000 years ago. And about 6,000 years ago, most of that glacial melt had happened. It had stopped and stabilized. And since then, you do see that there are changes in our sea level since then. But those changes in sea level are actually more to do with the response of the Earth than they are to the melting or addition of ice into the oceans. And when I say the response of the Earth, I'm talking about something called isostatic rebound. And isostatic rebound is a really fun and interesting process, and we're going to just do a little quick movie to show that to you right now. So this is a movie that we put together about what happens when you add ice onto an Earth surface, and as that ice then were to melt in the future, what happens to that Earth surface through time. So I'm going to start this movie. It starts 120,000 years ago, which was actually a period in time in Earth's history when things were a little warmer than today, which is kind of interesting to think about. So there were times when things were a little bit warmer than today. And as the Earth went into an ice age, which happened about 100,000 years ago, you're going to see that snow starts, and we're starting to build in this area, and you'll see that by about 75,000 years ago, we have an ice sheet that's pretty nicely built, and you'll see the response of the Earth is that it sags under that weight. So the lithosphere is pushed down as the asthenosphere responds, which is the liquid part, and moves way down. By 21,000 years ago, we have that massive ice sheet, and you'll see that the Earth has responded to that. And then you'll see as the ice sheet starts to melt, you'll see it moves into the ocean, and you'll see sea level starts to respond to that, but you also see the Earth's surface starting to respond. And so this is a response, as I mentioned, to the fact that the Earth takes on the weight of the ice, and then as that ice is melted away, it responds by moving back up. So somewhat like a waterbed. I just want to do a really quick return to that, because I also want to point out there's a lot that's going on in this particular graphic. Up here on the right, I'm pointing to an area where we're going to watch the ice sheet respond. Down below, you see sea level responding. As the ice adds, you'll see sea level drop. It started up above present day, then present day. Now it's fallen down below. It's down now to this 120 meters. So we know that time period because we just looked at a graph of that. So again, we're seeing this changes in things as we grow our ice and move it out of our ocean. Now we're going to be doing the reverse and popping it back in. So again, this is a lovely graphic to just kind of show that process of where we store our water on Earth, as well as how the Earth, the hard surface of the Earth, and the soft asthenosphere beneath it respond to that weight. Okay, so we've talked about what sea level is. We've talked about how we sit in relation to sea level. We've talked about how sea level has changed through time. Now we're going to think about the future and why do we care about sea level? So this is a graphic that is based on that same 2010 census data, and it's looking at projections for future sea levels. So you'll see this over here on the left, you'll see projected sea level by 2100. And this is in feet. And it's looking at our lowest projection. Now you'll notice that our lowest projection doesn't have no change. Our lowest projection has a change because we know there's enough heat stored up in our system that we are going to see sea level rise. These population numbers are from that 2010 census, by the way, just to remind you. So this is not looking, we're looking at the future in terms of sea level rise, but we're not looking at the future in terms of numbers. So basically from our lowest projection, which is 0.7 feet, so a little over a half a foot, all the way up to 6.6 feet, and that would affect almost 8 million individuals. And by the way, these projections are ones that New York is working with right now. They're looking at these same projections. These are standard projections for the Eastern Seaboard and not too much different from around the contiguous United States. Again, some areas will be affected just a little bit differently, but New York has taken these numbers as a very personal. We think this is where we are. So this graph only represents the United States in terms of numbers and in terms of impact. And just to remind you that there are more people that live on coastal zones around the world. So around the world, 250 million people live by the coast. And when they say coast in this numeric projection, they're looking at 5 meters, which is higher than what we're looking at. 16 feet is about 3 times as high as what we're looking at. So probably we would want to knock that number down if we wanted to look at similar impacts. But regardless, impacts are going to be large, and these are things that we need to be thinking about and paying attention to.
All right. So in thinking about how sea level is going to impact the United States and the world in the future, we are going to cast another poll. We want to know, do you think you will personally be affected by sea levels? Yes or no? So go ahead, fill out that poll, and we will be able to share the responses with you. I see that we don't have any questions right now, but if you do have any questions throughout the rest of the presentation, feel free to use the Q&A button at the very bottom of the Zoom window, and we'll be happy to answer it live or via text.
So overwhelming response here, 92% say yes, and 8% say no to the question of, do you think you will be personally affected by changing sea level?
Wow, okay, that's great. So 92% say that they will be impacted, even though if you think back to the earlier poll, many people were saying that they were not in a coastal county. So that is very interesting. If you are of the percentage, that 8% that don't think that you will be impacted, perhaps it is because maybe you live a little bit inland from that coast. And so we just wanted to address that bit. Margie, if you don't mind clicking to the next slide. Perfect. So there are a lot of people that live more inland, maybe in this extremely important food belt of the United States of America. And you might not think that sea level impacts you, but it actually does. It can impact you directly and indirectly. So directly, if you're thinking as a sea level, that salty seawater is rising, you can then be influenced or impacted by saltwater intrusion, which can directly negatively impact these agricultural fields. That increase of salt water will decrease production and kill off perhaps a lot of this extremely important food source. In addition, the saltwater intrusion can also contaminate reservoirs, which then threatens our water security and our food security. So that's just one way that it can directly impact people that are living more inland. And if we look at the next slide, even an indirect way that sea level can impact these extremely important productive areas of the United States is through imports and exports. So what you're looking at is a picture of the top US agricultural ports, and you can see all along the east, west coast, in this Gulf area as well. There are tons of ports that are extremely vital for exporting goods from the US and importing goods into the US. So the US Department of Commerce said that in 2011, 80% of exports and 70% of imports went through these water port areas. So if we're thinking about how sea level is impacting these coastal areas, they're directly threatening these ports, which then could influence less exports being sent out, which could impact the economy of some of these agricultural areas within the US. And it could also impact any imports that could be coming in. It could disrupt that. So if you think about all the goods and all the food that you have in your homes, a large portion of them are coming through these water ports. So they're extremely important.
So Laurel, I'm going to interrupt because there's a comment that came up here that I think would be if either you or Margie would want to address in the Q&A box. You might be able to see it, but I'll read it for everybody. It is hard to imagine how we all aren't going to be impacted by the massive costs of infrastructure, retrofits, and defensive structures. Not really a question, more of a comment, and I believe this was referring to the, even if you don't necessarily live on a coastline, that will be impacted. So I didn't know if you want to address that, or if you would like to, yeah, I just wanted to bring up that comment for participant. Deb.
I think that's an incredibly important comment, and all of us would absolutely reinforce that. We are connected.
There's nobody that's not going to be affected by this in some way, shape, or form. As Laurel just mentioned, all of our goods go through the ports. Infrastructure is going to be affected. Water resources will be affected. There's just really no part of our larger life that is not going to have some impact. So a very insightful comment. Okay, so how long have we been measuring sea level? Well, if you think about it, people have been measuring sea level probably for as long as they've been around, because we really like the coastal regions, as we've already pointed out. And because we like those regions, we need to know what's going on those waterfronts. But if we want to really look at how we've systematically been doing it, we have some really great records that go back about 200 years. So Thomas Jefferson was very much into trade and interest, and so he asked for a systematic assessment of our US coastlines. And so we have that wonderful data, which is terrific. It's nice to have these long-term data sets. Some places have been keeping it even longer than that, and I'm sure we all know that Amsterdam is sitting well below sea level. So of course that area has been focused on it for many years. And there are other areas as well, but it's certainly that's been important to people for a long time. I want to show you just some of the different tide gauges and ways that we measure sea level around the world. So I'm really going to focus in around the US actually. This is a cartoon that looks really crazy if you want to think about it. Like, here are these people that look as if they couldn't possibly be really doing this. They're hanging off of sections of wood or planks as they hammer things in place. There's one gentleman way down in a boat that's pushing up a stilling well, which is a tube that we put into the ocean, and the tide gauge goes into it to protect it from all of the currents and wave action, so that it's a little bit easier to read. Again, this looks extremely dramatic. This was drawn in 1950 by somebody that actually was part of setting in place some of these tidal gauges. So I'm going to show you a couple, just so remember, get this imprint in your brain. And now we're going to go to 1915. This is in Prince of Wales Island, Alaska. And again, I'm pointing out these are like logs that have been pushed down here to help support this. This gentleman has come across what looks like very large steps on a very rough hewn ladder. You can see that stilling well support that's right here. And you can see this incredible meter stick that's here to help measure the tides. And this guy has, come out to just check on his equipment. So, 1915 wasn't too far before the 1950s. And so this looks just as crazy as that last one. And I'm going to show you one other one, which I really love. And this is, again, in Alaska. This is in 1939. And to actually get to their equipment, they had to crawl down this 60-foot ladder, which is suspended by wires and stakes. Imagine doing that. All right, now you've imagined doing that. Now I'm going to add a little bit more information to this. In Alaska, the tidal extremes are huge. So the difference between low tide and high tide can be very extreme. And so you might be all the way down here and a high tide is on its way. I'm going to point out to you how high those tides can be. So there is a range of 12 meters or almost 40 feet between low and high tide. This is in Anchorage. So when I was in Anchorage a few years ago, there were notes up all along the waterfront that said, don't walk out onto the mudflats during low tide. People are killed here regularly. And this is why, because these tidal extremes are so significant. So it's setting tide gauges in early times was not for the faint of heart. It's gotten a little bit easier. Now this is current day. This is New York. This is the tip of the battery. And this is our tidal station down there. And this has been collecting data consistently since 1920. And over here, you see a satellite. So we have several satellites that help us with collecting data, and they measure down to the surface of the ocean. And that helps us to get this absolute sea level that we've talked about. Again, that global sea level. And we actually combine the data between tide gauges and satellites to get a better sense of what's going on in our oceans. We've had satellite data since 1993, just to kind of put that into context. So couple of hundred years we've been collecting data, but only since 1993 have we been able to use satellites to add to that. Okay, so what have we learned in all that period of time? This is a graph of average global sea level, and it's put together from multiple data sets. And what I'd like to do is ask you to put into the chat one or two things that you notice about this particular data set. So anything that pops to you in this data set. And while you're doing that, I'm going to just walk us through. So earlier we looked at something that went back 21,000 years. This period of time is only a little over 100 years. So it's moving from 1900 over to 2010. So it's also set up differently than that prior graph. If you remember, that one had present day on the far right and went back in time. This one's marching forward in time the way that we're probably more used to seeing things. And our y-axis is looking at global sea level. So again, this is absolute sea level. And it's relative to an average that was taken 1900 to 1905. And this is in millimeters. So last time you remember we were looking at meters of change. This is in millimeters as we move forward, millimeters per year. I'm going to ask Cassie, are there any responses from people as to what they are seeing in this graph?
Yes, so we have just a point of clarification for our attendees. We have disabled the chat box, so you should be using the Q&A box.
Sorry.
No worries. I just wanted to make sure everyone is clear on that. So you can type your answer right into the Q&A box. So we have one participant who says that there seems to be a rapid rise in recent years. And there's a question, what are the different line colors? So maybe Margie, if you could walk us through that, and maybe we'll get some more answers.
Absolutely. So the different line colors are different people have worked on this data and put together this trend. And so what I want to point out is that even though there are different science teams that have worked on these and taken the data and tried to put them, so there is some averaging that needs to happen. And so different groups have worked with the data. You'll see there are some slight differences, but you'll also see that they all tend to be moving in the same direction. Are there any other observations or?
Yep, so it looks like there is a steady rise sort of overall. However, perhaps some more rapid rise in the recent years. And then with the comment was with different groups, you can see verification of the rise in sea level, perhaps the grouping of the lines. Yeah, so those are our answers.
Those are
and then one last one. I would say the rise is increasing in the last 40 years. And then there is a question about, curious what happened in 1930. I think they're talking about that dip and that yellow line there.
Ah, okay.
Yeah.
Yeah, I'm not sure. I'm sorry, I'm not going to be able to answer that. I don't know without going back and looking myself. I couldn't answer that. So I apologize for not being able to answer that, but that's a really good thing for us to look up. Maybe when this video gets posted, I can just post an answer to that. Or you can send your email and we'll get back to you on that. But in terms of kind of taking a look at this graph, you guys addressed some very important things. I wanted to point out that this red is satellite altimetry data. And so if you remember, 1993 is when our satellites started to help with data collection. And so prior to that, we're looking at tide gauges, and those are averaged together and worked on. And again, that's why we have these small differences between the different data sets. The gray shading, which nobody mentioned, but I wanted to point out that gray shading is uncertainty. So you'll see there's a much larger uncertainty as we go back in time. And then as we move forward and you follow along with me and we get to this satellite data in recent years, much more minimal uncertainty. And actually our satellite data has a 1 millimeter uncertainty range. So that's a very, very small amount based on prior So thank you for that. That was great. Did you
So
want to
Margie,
say something?
yeah. So since we're on this slide, I did want to bring up the questions that were specific to the slide.
Okay.
So the first comment / question is, although the trend is upwards, it seems to be, there seems to be dips. Could this be seasonal? So that's the first question. I'll let you.
Absolutely. Absolutely. Yeah. So there is a seasonal variation that goes along with this. This has been averaged out a little bit, so it's not quite as bumpy as you might see. But if we were to really look fine-tune at the data, you would see that seasonality very specifically. It also can have to do with, so there are also trends that happen over several years. You might have, you know, a very cool season. You can have El Niños and La Niñas that affect. So again, it's not just seasonal, but that is absolutely part of this story.
Okay, great. And the next question is, would you consider this exponential growth?
I would, yes. It's very definitely on a strong trend, and you can see, and you see up here actually, from what we have been able to determine, that we are definitely accelerating from the 1990s upwards. So definitely.
Okay, great. Thank you. And were each of these data sets collected from different locations?
No, so this is global data set. So this is looking at tide gauge data globally. It's just in how the data was actually worked through with the group. So there are adjustments that have to be made with tide gauge data. You can't just read it straight out. There's things that happen on coastal waterfronts that you have to be aware of. And so that's why you get these small differences.
Right. And the last question is the water level at the same times of the day? And there seems to be quite variance.
Are the water levels at the same time of the day? So these are average. So they would be looking at through a cycle. So if they would take the average of the day, if that makes sense, rather than looking at a specific time period in the day. Okay.
All right,
so
great. Yeah, that's, yeah.
Okay.
So Margie, I think we can see you now, but we have a different view of the slides. So I'm gonna unshare your screen, and then if you could share your screen, if I can, let's see here.
So I can stop sharing.
And then if you want to get back into the shared screen again, here. Move your camera up so that we could see you.
Sorry.
There we go. And then no worries. And then if you can't share, I'm happy to share and I can get to the slide.
You know what? At this particular moment, I am having trouble with this. So if you don't mind sharing, that would be great.
I will share my screen, and that way we can keep your video on.
Great,
and
thanks.
then let me just, and you can see this just okay?
That's great. Yeah,
yep.
I can see
okay,
it.
Great. So I will.
We're at slide 20.
Okay.
Yeah. And Laurel's going to talk.
So we just looked at like global sea level, and now we're going to look a little bit more local. And since Lamont is based in New York, we're going to focus on New York City. We're just about 30 miles away from New York City. And so just as a couple slides back, Margie showed you the tide gauge at the Battery, which is at the tip of Manhattan. So now we're looking at the data collected from that tide gauge. I wanted to draw your attention to the y-axis is in meters. The x-axis is in years. And a couple things that really are amazing about this data is that it is long-term. It starts way back around 1855 all the way to today in 2020. And that is so critical for looking at any type of climate data, whether it be temperature or storms or sea level rise. You really need that long-term data set to make any definitive statements or draw conclusions about the data. So this is great that we have this. And you can see from this long-term data set, that trend line is going up, which is similar to what we saw in the previous graph. We're seeing that increase in sea level. So specifically, our relative sea level in New York, or our local sea level, is trending upwards 2.87 millimeters per year, and that's with 95% confidence. That is, it may not seem like a lot, but it is when you think of we're about the global average, which is 3 millimeters per year increase in sea level, and that is a ton of water volume. While the rise doesn't seem like it's that much, the water volume is immense. And so just as you guys pointed out, you're very noticing the data has that variability, that it goes through these up and down patterns, and the last data set was a little bit more smooth, as Margie mentioned, and you can really see the yearly, seasonally, even daily changes due to the tides. But that is why it is so important to look at that long-term data. So like, for example, if we were to look just within the last decade, it might not tell the full story. But if you're looking back all the way back to before this data gap here, you can really see that trend line is increasing. Something else that really popped to me is that we do have this little gap here. That was so far back in time. It could have been equipment failure, or the maintenance of that data or of that equipment wasn't maintained. Hard to say, but thank goodness we do have this long-term data, so we can still see that very significant trend line increasing. Just a couple things I want to point out. Okay, if we go to the next slide, we are going to look at what is driving sea level rise. So if we're looking at this time range from 1992 to 2010, you can see that sea level rise is really driven by two primary causes, and it was almost 50% each. So thermal expansion causing sea level rise at 50%, and the melting of ice on land is about 50%. So thermal expansion is water's response to thermal energy, or heat. So as that water is heated up, you're exciting those water molecules and they start to expand. This is easily viewed right here in this thermometer picture to your right. So that drives 50% of sea level rise during this time period. The other 50% was from the melting of glaciers. So smaller glaciers are found all over the world, on every continent except for Australia. So there is a lot of ice there that contributes towards 27%. And then we have two huge ice sheets on our planet today. The largest is in Antarctica, or the South Pole, and the second largest is Greenland in the Arctic. So those both have a ton of water and have been contributing 12% and 9% towards sea level rise during this time period. Okay, you can see that this time period ends at 2010. So now, what's happened in the past decade? Perfect. So in the last decade, things have started to shift a little bit. Now this data has been pulled from the IPCC, and you can see that the melting of land ice, so glaciers and the Antarctic and Greenland ice sheet, now cumulatively contribute approximately, or 62% of sea level rise. So you can see now that's even more than 50%. They're the primary driver, and thermal expansion has dropped down to 38%. Both are significant, but with our warming world, you can see that the melting of the ice in regions all over the world, especially our polar regions, are contributing heavily to sea level rise. You can click to the next slide. Thank you. So in looking at these glaciers in comparison to ice sheets, they are relatively smaller. So of all the glaciers, there is a 0.3 to 0.5 meters of sea level rise. That is significant. Don't get me wrong. That is quite a lot of sea level increase. However, the ice sheets, they have so much water tied up on land that they tell an even bigger story. If we go to the next slide, I can show you an image of both Antarctica and Greenland. Perfect. So remember, Antarctica is the South Pole, the very bottom of our world. And we split up Antarctica into two pieces. So we have West Antarctica on the left side and East Antarctica on the right. West Antarctica is a smaller, and it contributes, if all of the ice on West Antarctica were to melt, it would contribute 6.5 meters or 21 feet of sea level rise. East Antarctica is quite large, that contribution would be 52 meters or 170 feet of sea level rise. So if you combine all of that together, that is a large contribution of 191 feet of sea level increase. And just for reference, the Statue of Liberty is about 151 feet tall. So that is even taller than the Statue of Liberty in terms of water that would be added to our oceans. Greenland is contributing 7.3 meters or 24 feet. So in total, we are looking at over 200 feet of sea level rise. It just goes to show how much water is tied up into these huge ice sheets. But I want you guys to remember that these ice sheets have been around for millions of years. So it's not like we are going to be seeing the entire melt of both of these ice sheets tomorrow or even in the near future. But our warming world is impacting some hot spots in the ice sheet, so along the coasts of West Antarctica particularly, and Greenland. And that's why our colleagues are specifically focusing on these polar regions in terms of how fast that ice is flowing and melting and what it's contributing to sea level rise. Next slide, please. Okay, now Margie is going to explain how we're going to run through our Polar Explorer explorations.
Sounds great. So for those of you who want to do this on your smartphone, we'd love for you to actually do this with us. So if you could use this URL, it's pretty straightforward, polar/explorer.org with a backslash. You can do it on your computer if you want to open a second window on your computer. Or on your smartphone, and then you can move along with us. We'll be projecting it so that you will be able to participate with us if you don't have a smartphone or whatever, but it is way more fun to actually interact with us. It's an interactive app so that you can explore on your own. We're just gonna launch you in with a few questions. And Cassie, I think we're gonna stop sharing and let Laurel go live with the browser.
There we go.
Perfect.
Can you guys see everything all right?
Yeah, we can. Sorry.
Okay, good. I was like, oh, I don't know if they can answer.
I forgot.
Okay.
So first of all, this is a map-based app. And so it's what we call a data visualization, where we actually put the data into the map so that you can actually learn from exploring the map itself. It's a really fun tool that has a variety of different pieces to it. Laurel just pulled up one of the maps in what is sea level. She's looking at elevations beneath the sea. So just so you know, the whole app is set up as questions, a series of questions that drive you into a set of maps. So what is sea level is the question, and then there are 3 different maps that you could jump into. We picked elevations beneath the sea. And if you wanted to click on anywhere on this map, it would actually bring you up with a number. And that number is telling you what that elevation is beneath the sea. So you're going to see that these are negative numbers. Laurel's zooming in, so you can see we're down off the US coast and we're down negative 5,000 meters. You'll see there's a kind of a lighter fringe area along the edge of our coastline. That's our wonderful continental shelf. And generally continental shelves are only 100 to 200 meters deep. There are a couple of exceptions. Antarctica is an exceptional area that has a very deep coast, continental shelf, excuse me. But this shows you this wonderful grading. So our continental shelves are actually part of the continent. They're not really considered part of the deep ocean, but they're underwater right now. And we've talked about that already. They're underwater because we have moved ice off of the polar regions into the ocean. Okay, so other things that we want to point out here, you have your menu bar on the right, you have a plus and minus up on the top left, which allows you to zoom in or out. There is, on the menu bar, you'll see a little I button that shows up. If you were to click on that, it takes you to an information page. We're not going to spend time on information pages today, but there's a little bit more information about each of these topics in the information page. And earlier, Laurel clicked away another piece, so maybe, yeah. There's a little write-up that explains a little bit more about the maps. We don't need to worry about that today because you're with us. But if you were exploring this on your own, you might want to take advantage of that. And also there is an audio that you could click on the bottom of that. Again, we're not going to do that today, but it talks you through a little bit more of the story. So multiple layers of information. Okay, I think we're ready to do our first exploration.
Perfect. And one more thing, if you're curious about what this bar does, it just increases the transparency of that layer so you can look at the base map. So if you ever wanted to compare what data you're looking at and where it overlies, you can feel free to play with that. All right, so let's start at the very beginning. Everyone, please click on where is sea level changing now? Then we're going to click on tide stations, recording, rising and falling. Once you click on that, feel free to X out of that description. You can even hide this bar for now. And what you're going to be looking at is a map of the world and all these different tide stations, tide gauge stations all over, and they all are associated with a different color. So if we zoom in a little bit to the US, you can see that there's a lot of different colors. There's greens, there's yellows, there's reds. And if you look up to the legend at the top left, you can see that it's all associating with a sea level range, sea level change range. For example, since we live in New York, I'm going to click on the battery and you can see it tells you what the tide station is, what the sea level change is. So for us, as we mentioned before, we're increasing at 2.84 millimeters per year. And you can look at the measurement period as well. So what I want you guys to do is start exploring, start clicking around these different tide gauges, and in the Q&A, write in one tide gauge that really stands out to you, something that is so surprising, and tell me what the sea level change is of that tide station. While you guys do that, I'm just going to start clicking around a couple things that were interesting to me. So up in New York, we have the Hudson River estuary. I'm going to go into the Chesapeake Bay estuary here, and it's much different. So you can see that these sea level changes are more than what we're seeing in New York. All these are in that yellow range, so 3.72. That is, again, greater than the global average of 3 millimeters per year, which for reference is about 3 rice grains stacked up on top of each other. This is a bit of a hot spot here, 6.02 millimeters per year, and that's the Chesapeake Bay Bridge Tunnel, Virginia. Zoom out a little bit. Let's see. I'm having a hard time seeing if there are any question or answers, but Cassie, I'll let you take that.
So there's one comment. So Port Angeles, Washington, actually looks like it's declining. And the participant has said, I assume isostatic rebound is behind that. Another participant has said Bridgeport, Connecticut seems interesting. Skagway, Alaska, probably the lowest change in tides in the world. And then there's a question that has come up about does shifting of the Earth's tectonic plates have any impact on sea level? So those are just a few of the responses.
Oh, great. You guys have pointed out a lot of things that I were hoping you would see. Let me zoom out a bit. Someone said, would the plate boundaries impact? And so one in particular that I think is quite interesting is Skagway, Alaska. So you guys could see that their sea level is dropping, or it appears to be dropping quite drastically. And this is a little bit different of a story than like some of these would be isostatic rebound driven. This is actually on a plate boundary. So as the plates are colliding, you see a part of that land is starting to rise up and causing it to look as if the sea level is dropping. But remember that from thermal expansion and the contribution of the melting of land ice, the sea level is not dropping. The total sea level is increasing. It just, the relative sea level in this area looks as if it is dropping. Great question. Great observations.
Another comment is Eugene Island, Louisiana, with 9.65 millimeters a year. I'm curious if the population is changing in that area. And then Scandinavian countries seem to have recorded a lot of negative change.
Wow, you guys are popping out some things that I hoping you would see. Absolutely. So areas in Alaska, areas in Scandinavian countries, they are looking like they're dropping, and that is due to the isostatic rebound that Margie was talking about earlier. So the fact that without the heavy weight of that ice pressing down on the land, now this land is starting to rebound or rise back up, making it seem like sea level is dropping in those areas. In Louisiana, this is an extremely vulnerable area in the US with 9.65 millimeters per year of sea level rise. And that's, of course, due to the rising of sea levels, but also this area is eroding. So the weathering of the land can contribute to the perception of sea level rising even greater in this area, as well as subsidence, so the sinking of the land. And if you zoom in, you can see that they're kind of in this delta area. So the land is extremely close to sea level as is. It's very, very low lying. And you mentioned, if you were wondering if the population density was increasing in that area, I don't think this is something we're going to be able to get to today, but there is an area in Polar Explorer that you can look at population density, and you can compare it with the tide gauge changes to see the areas that are most vulnerable and the populations that would be hit the greatest with sea level rise. Great questions. Okay, so we popped out a lot of things. I want to move on to the next bit. So now we're going to open up our menu again. Quickly go back to the main menu, click on why does sea level change? And then click on the role of the oceans. Internal temperature, present. Now we're gonna pop up with this map here. Again, these temperatures, if you click around, it's gonna pop up with the temperatures in degrees Celsius, comparable to the legend at the top left. We're going to, zoom out a little bit. No surprise that the equator area has really high temperatures. The polar regions have cooler temperatures. The investigation I want you guys to do is dive into the ocean. So right now we're looking at the surface of the ocean. If we dive down at 50 meters depth, how does the temperature change? What if we go to 100 meters? Changes even more. Please write in the Q&A, where do you see the last persistent warm feature in the ocean? At what depth does that disappear? So I'll do it with you guys as you explore. We're at the surface here. Surface is very warm, the surface of the ocean, because of that interaction with the sun and the atmosphere warming that surface ocean. So of course it's going to be very warm. As we dive deeper, it's starting to cool off a little bit more. You can see these temperatures are changing. At 100 meters depth, even less. Let's keep going to 200. You can really see we don't see any areas of the globe that have that hot red sections, but we do still see some orange. We can see our ocean gyres. Right here, this is very interesting, and perhaps you guys have found this too, is that everything is much cooler, only blue tones, except for this interesting ocean feature here. If anyone knows what this is, they can pop it up in the Q&A. And then there's also this interesting feature right here that is still holding on to its temperature, that orange coloration. So that's at 500 meters. And then at 1,000, we lose that warm feature. So Cassie, does anyone know what this is?
We have a couple of answers. The Bermuda Triangle, hurricane activity, the Pacific Garbage Patch, the Gulf Stream, Bermuda Triangle.
Gulf Stream.
Sargasso Sea. Okay, all right, great.
It is the Gulf Stream. And oops, I did not mean to do that. I meant to zoom in. This is such an important feature for us on the East Coast. It's bringing warm water up from the Caribbean, shooting it right up the East Coast of the US, and then bringing warm water all the way over to Europe. So the temperatures, meant to zoom out. The temperatures of our ocean would be much colder without this Gulf Stream and this persistent warm feature that goes all the way down to 500 meters depth. It's quite amazing. And that's why our waters are warmer at the same latitude as the West Coast that has much colder water. It's because we have this nice warm Gulf Stream feature, and it makes our marine environment very unique. This is the Red Sea. So that is like a more trapped, closed inlet body of water, so it doesn't have as much ocean flow. It keeps the water temperature quite high in that region, even at deep depths. But I think everyone can agree that at this somewhere between 500 to 1,000, we lose that last persistent feature of the ocean. And so this is related to sea level because we talked about thermal expansion as being a huge driver of sea level rise. And so at the surface, you can see the warmest temperatures because it's so close to the atmosphere interaction in the sun. But there is still so much ocean water that has yet to be influenced by rising temperatures. So it just shows how much ocean is still available for warming. And the IPCC stated that as warming of the deeper ocean due to pressure occurs, the thermal expansion is even greater than at the surface. So for the same amount of warming at the surface, it would be a greater expansion at depth because of pressure. So that's something that we need to consider. We need to think about the ocean being a huge sink for temperatures and how there's still so much ocean left that could be warmed and increase sea level due to thermal expansion. Great job, guys. I know we are at 3 o'clock right now. Margie, do you think that we should move on to who's vulnerable, or should I?
I think we should do who's vulnerable,
Okay.
just to show that aspect of the app, if you don't mind.
Absolutely.
So there are a variety of different, I like to think of it as a book with chapters. There are a variety of different chapters in the app, and there's one whole section on who's vulnerable, which if you go back to your beginning in the toolbar, you'll be able to find it at the bottom. And the who's vulnerable looks at everything from where our population density is, where we've impacted the earth, to looking at atoll regions, etc. We are going to look at, right, thank you, who's at risk from floods. So you want to click on that one. it's like having a live feature here. And we're going to look at 2 different maps together. We're just going to click back and forth and get some visuals on them. We're going to look at economic impact of floods, and this is worldwide. And then we're going to shift back and look at mortality from floods, because I think it's really fascinating to kind of look between the two. So in this app, set of maps, the red is where we see the most significant impacts, and the blue would be less significant. There's still impacts, but less significant. So it goes blue, yellow, red. And so right now we're looking at flood mortality. And I want you to just look at the US in terms of impact. So definitely an impact. Certainly there is going to be some mortality, but nowhere as severe as if we go down to South America and we look at maybe if we just stay in that hemisphere, that might be the easiest. So South America versus the US, and we're just going to look at huge mortality impacts down in South America. And now let's click back to the economic loss map, just for a bit of a quick comparison. And you see the difference. You see that in the United States, the economic impact on our East Coast is significant, much more significant than our mortality was. And yet the response in the South American or the Southern Hemisphere is the opposite. You're seeing that they are much more impacted by mortality. You saw that much redder section down there than they are with economic loss. And I think that that's not at all surprising, given infrastructure, given our different economic base in our countries. We need to be aware of this, that everybody is not in the same footing. So the vulnerable communities are situated all around the world, and vulnerability plays in at multiple levels. So just because we're economically vulnerable, our mortality numbers are much higher. Now, granted, if we went into specific communities, we would still see that there would be major differences in terms of mortality as well as economic. But this is kind of an interesting set of maps for you to be able to explore and look at specific impacts. I think that's a really an interesting opportunity for students to really spend some time in there. So with that, I think that I see there are a couple of questions which we can answer if we want, if we have a minute. Would that be okay, Cassie?
Yes, go ahead. And so if you can see the questions, I'm happy for you to take over. For our viewers who, if you do need to leave, just a reminder that this is definitely being recorded, and we'll share the session with you when it's all set. So Margie and
Actually,
Laurel, if you want to take it away.
Before people leave, I did want to say one thing. I think Laurel and I both felt really committed to making sure that we end on a positive note. So we are definitely aware that sea level is rising. We've already talked about the fact that there is, Laurel made an excellent point already about that there's water, there's heat in the pipeline, and we're going to see changes. But it's not set in stone. We definitely have the ability to create change, and I think we want to do that. So the small changes that we make are critically important, and talking about it with our students, if we're teachers, and if you're students, talking with your friends, creating change, that's really where we need to be right now. So before anybody hangs up or moves on, we really want to make sure that we ended with that. And then we can go back and we can kind of address some of these questions. So Amy had asked, could the economic risk from flooding be a driver for environmental change in our government? Interesting. So I think that's a really interesting point. People do often respond more to economics than perhaps they do to science. And you know, this is just different people have different touch points. So I think being able to explain on multiple levels is really important. So Amy, I 100% support that as a concept. I think that the military has been very aware of sea level rise because of safety, security, and economic impacts. So this is happening. It's not something that is hidden from people. Mm-hmm. I see, do geothermal vents underwater create warm areas even near the bottom of the ocean? They absolutely do warm locally, but it's not a strong enough influence to really have a regional impact. So we wouldn't pick it out on these larger scale maps. But if we were to zoom in on specific areas, absolutely, hydrothermal vents are a great source of heat. And in fact, a colleague and I did an activity around that once. So fun things. Are there other questions? Or just, I see a couple of wonderful things.
A lot of kudos.
So that's great. I think the app itself, there's so much to explore. So I really would love for you to take time, explore it. If you have questions, reach out. I did answer Beth about the 1930s dip. I did a quick recon while Laura was talking and couldn't really find anywhere where there was a definitive answer, except that there was a cooling in the Northern Hemisphere, and there are lots of opinions as to why. So perhaps we can just end with that and we'll do some more work. And if we find something else, we can go forward. But I'm really glad you like the app. Thank you, Laurel. And I really enjoyed being here today. So turn it back to you, Cassie.
Yeah, thank you, everyone.
Great. Thank you so much to our presenters and for our very great questions from our audience and comments. As I said, we will be sharing the recording of this video along with additional resources that Margie and Laurel have put together, and we'll resend the link for the web-based browser so that you can continue to explore this more on your own or with your students in your classrooms. If you do have any questions for Laurel or Margie, please do not hesitate to get in touch with me. I'm happy to pass along questions. And just as a little plug, Laurel is going to be back later in June to do a glacier goo session for us for a younger audience. But if you are so inclined, please join us for that. All of the remaining EI Live K-12 sessions for June are posted on our site. And again, if you have any questions, just get in touch with me. So thank you again, ladies, and enjoy the rest of your day. Thank you to our viewers. All right, have a good day, everybody.
Thank you.